Good morning, dear students.
Good morning, ma'am.
So, today we are going to start with today this session with again discussing about the test bench, VHDL code. Okay. So, as we have discussed about various testing methods of logic circuits. So, in continuation with that, we are discussing about test bench, okay, which is nothing but a VHDL code which is associated with particular VHDL code. Okay, so that means if we have written any code for particular application or particular circuitry, so that is tested with a test bench which is associated with that entity. So earlier we have discussed about what is the test bench of half adder and what is the test bench of full adder. Okay. Also in the yesterday's practical, we have simulated that code also. Okay. So from that you must have got idea about how to write a test bench and then how it works. Okay. So that we have seen in the yesterday's lecture. So now today we are going to see what is the test bench or how to write a test bench for comparator circuitry. So let us start with that. So I'll share my screen. So as we have already discussed about VHDL code of comparator. So comparator here we have considered 4-bit comparator. Okay. So for A and B. So these two uh, numbers that we are going to compare. Okay, so these are 4-bit. So here, for whenever we are writing or declaring ports, these input ports A and B, so that time we need to consider a vector because we are considering it as a 4-bit. So here you can see that first there is a library initialization. So library declared and then uh, this packages that are added to that program. Okay. So after that, in an entity declaration, here you can see that for the port, okay, so after that library declaration, we write entity for the comparator is, and then after that, we are declaring ports. Okay. So here, as we are comparing these two bits, so there will be two input ports and there are 4 bits. So we need to specify it, that is a std underscore logic underscore vector. Okay, so remember that here we are considering is as a vector. Okay, so that means we are considering these are the bus. Okay, and these are 4 bits. So here the range is from 3 down to 0. Okay, and then as we are comparing, so we will get three results. One is that there is if the number is greater than, or if it is less than, or it is equal. Okay, so we have three output pins for this circuitries, that is GR, then LS and EQ. These are the three output ports. And now as these are only bit, okay, that means if A is greater than B, then only, we are going to get the result in a single bit. So these are single bit number outputs. So the type that is specified as a std underscore logic. Okay, so here this is about the port declaration of the entity comparator. Okay, so that means there are actually overall 5 ports, 2 input ports and 3 output ports. Okay, the input ports, these are the vectors, that means they are more than 1 bit. So we have, as here in this case it is a 4-bit. Okay, so this is about the entity declaration. After that we are ending this entity, that is a end comparator. Okay. And after that what we need to do, we need to declare a architecture. Okay, so here uh, architecture, okay, behavioral of comparator is, and then we will start to write the architecture. So it is a begin of, so we need to start with the keyword, that is a begin. And after that, as we want all this expression that should be executed sequentially, so we will write a process inside this architecture. So process, and the sensitivity elements, that means the sensitivity elements which are going to change within this process, that are A and B. Okay, that means only these inputs are going to change, and we have those many inputs only, so they may change while simulating. So we are considering this as a sensitivity element, and so that are written in the bracket. So process A comma B, and then begin of this process. Okay. Now what we want, if A is greater than B, then we want that greater, that is a greater than. So GR input that should be high. Okay. If A is less than B, then we want less than should be at a high logic level, and others should be at a low logic level. Otherwise, now if both these conditions are false, then what should happen? Equal to should be high. That means EQ should be at a high logic level, and others should be at a low logic level. Now, whenever we discussed VHDL code of comparator, that time we have considered only one output. Okay, others we have not considered. We just stated that greater than, that is a GR that is equal to 1, or less than equal to 1, or equal to 1, depending on how it is giving the output. Okay, or what is the result of the comparison. But at that time, uh, we have not considered others output. Okay, but it is needed that that should be clearly specified. Otherwise, when you simulate that program, that time it will result as both these outputs. That means if A is greater than B, okay, so that you require that greater than that should be equal to 1. At the same time, LS and EQ that should be equal to 0. Otherwise, it will be result as a uninitialized, that is a U, or undetermined. And that should not be the case. So that may result in some wrong output, and that is why it is required that you should clearly mention what about the others output also. Okay, so that is why in this program I have made certain modification than that of earlier program, that greater than that is equal to 1, okay, that is assigned to one value, ls that is assigned to 0, and eq that is assigned to also 0. When this will happen? If A is greater than B, then this will happen. If this condition is false, then that means what will happen then? B will be greater than A, or you can say it as A is less than B. Then greater than, that is a GR should be 0, less should be equal to 1, and EQ that should be equal to 0. Okay, so this is the another condition, and if both these conditions are false, then GR should be equal to 0, LS should be equal to 0, and EQ that should be equal to 1. Okay, so after this we have to end of this if loop, then end of end if, then end of the process, and end of the behavioral. Okay, I think almost all of you are aware about this VHDL code. Now what we are going to do, we are going to write a test bench for this code. Okay, so how to write test bench? So we need to write a stimulus process. Okay.
एक्सक्यूज
Yes.
मी मॅम.
Yes.
मॅम वेटिंग रूम चेक करा ना.
Yes. No one is there in the waiting room. No one. Uh, someone's asked you. Asked you.
येस मॅम.
Okay. Um, I hope they have joined now. Okay. So what is mean by test bench? As I earlier said, it is the code which will test this code, that is a whatever VHDL code that we have written. Okay, so for that we need to give certain inputs, and then depending on that inputs it will give us certain outputs, and from that we can verify that whether the code that we have written is correct or not. Okay, so that means we are simulating that code, and from that we are deciding whether the code that we have written is correct or not. Okay, so here uh, the test bench for this code that we have earlier written. So whenever, now as you have seen, while actually using a Xylene software, ISC software, that time when you write a test bench for any code, so we need to associate that code with a test bench. Okay, and when you do this, all these entity library declaration, then entity declaration, that parts that automatically comes. Okay, but if that is not the case, so we need to write it, and so we have this code here. So library, IEEE and package, that will be automatically added. At the same time, we have used this another two packages, that is a std underscore logic underscore arithmetic and std underscore logic underscore unsigned. Okay, so these packages that will be automatically added to this test bench. Okay, when you are associating that VHDL code with this test bench, then we are writing the entity for this VHDL कोड. म्हणजे आता आपण काय करणार आहे, हा जो काही VHDL टेस्ट बेंच कोड लिहिणार आहे त्याच्यासाठीची एंटिटी. बट इन दॅट एंटिटी यू डोंट नीड टू डिक्लेअर एनी पोर्ट. Okay, because we are instantiating that all things from the VHDL code of the comparator. Okay, so in a test bench there is in a entity there is no any need to declare ports. Okay, after that architecture of this test bench. Okay, so whatever is entity test bench, so here architecture behavior of now, as I have given the name for this test bench as a test bench only, so is, and after that there will be signal declaration. Okay, so that is signal a comma b, that are std logic actually there should be component. Okay, component, as we are this, I'll make it correct. Let it be now. I will correct it while sharing these ppts, but now here there should be component declaration. Okay, so we are going to have a component that is a comparator here, and then for that comparator, that declarations are a signal a comma b. These are the, sorry, then there will be ports. Okay, so that ports that will be completely, I have missed that part here in this ppt, but let us discuss that. So that component declaration, so that whatever are the ports of the comparator, that is a b, both are the inputs, and that are the std underscore logic underscore vector of, that is a 3 down to 0, that range, and outputs, that are the gr, ls and uq, that are the out, and it is of the std underscore logic. uh, so all are the bit ports. Okay, so then it will be end of that component. Okay, and after that we need to, now whatever are the signals that are present in this trace bench, that we need to डिक्लेअर. ओके, म्हणजे काय करायचं, करावं लागेल आपल्याला, आधी आपल्याला कंपोनंट डिक्लेअर करून घ्यावं लागेल, आणि त्याच्यानंतर मग आपण या टेस्ट बेंच मध्ये कुठले जे काही सिग्नल्स आहेत दॅट वी नीड टू असाइन. ओके, so here in this there are signal a comma b, that is std underscore logic underscore vector 3 down to 0, and initial value for this is assigned as a 0. Okay, so all these uh, signals that will have, and all the bits in this a and b signal, that will be assigned to 0. Okay, then after that signal GR, LS and EQ. That is again of a STD underscore logic. That means it is a single bit and it is again assigned to 0. So that means we are resetting this component here and we are keeping all this values signal at a 0 level. Okay. And after that we now need to instantiate that component. So what we are instantiating a comparator. So that means we are instantiating that comparator. So we are going to map the ports of that component, that is the A, B, GR, LS and EQ. All these ports will be mapped with the ports of this unit under test. Okay. And after that we are going for the simulation process. Okay. So that means we are going to stimulate inputs. Okay. And for that we are now going to write a process. Okay. So that process, the name to that process, that is given as a TB. And now we need to begin with the that process. Okay. So now here A is assigned. So now what we are going to do, we are going to give certain inputs to the inputs of this comparator circuitry, and from that after uh, simulating this test bench we will get the result. Okay. So first case I will consider it as a, first I will give A that is equal to 0010. Okay. So that means it is if you are considering it in a decimal, it is a equal to 2. Okay. And then I will have the value for B, that is a 1001. So that means it is equal to 9. So that means what should be the result of the comparison between A and B? What should be result?
B is greater than A.
B is greater than A. That means actually in this case we should get the result as LS should be equal to 1 and great GR that should be 0 and EQ that should be 0. Okay. Because A is less than B. Okay. Now we will hold this values for 2 nanoseconds. Okay. Now you can keep this period okay as much you want. So I have here in this case I have mentioned it as a 2 nanosecond, but you can keep it for 100 nanosecond also, 200 nanosecond also. That means for how much time you are waiting, so that much time will be there for holding these values. Okay. So for that much time it simulator will hold these values for A and B, and then it will go for the next. Okay. So here I have considered it as a 2 nanosecond. Okay. 2 nanosecond नंतर काय होणार आहे, तुमच्या values change होतील. So now it has been changed to A is equal to 1001, that means 9. Okay. And B is changed to 0010. Now that means B will be equal to 2. So in this case, what should be result?
GR is equal to 1, LS is equal to 0 and EQ is equal to 0.
Yes, that should be the result. So that means here GR that should be equal to 1. So now here you must have observed that as this is a vector, so that means there are A and B both are vectors. Whenever we are initializing constant value to these variables, so we have stated it in a double quote. Okay. जर सिंगल बिट असेल तर आपण तो सिंगल कोट मध्ये करतो, पण इफ मोर दॅन नंबर ऑफ वन बिट इज देअर, सो इट शुड बी रिटर्न इन अ डबल कोट. ओके. तर तुम्ही इथे जर ऑब्झर्व केलं असेल तर तुमच्या लक्षात येईल की आपण इथे या सगळ्या व्हॅल्यूज काय केलं, डबल कोट मध्ये लिहिलेले आहेत. ओके. सो while writing VHDL code in a Xilinx, you need to take care for this. Okay. So here again we are going to wait for 2 nanoseconds. That means these values will be hold for 2 nanoseconds, and then we are initializing some more values. That is A is equal to 1010. That means A is equal to 10, and now B is equal to again 1010. So that means we are assigning value for B, that is Again it is equal to 10. So now in this case our result should be, what should be our result?
GR is equal to 0, LS is equal to 0, EQ is equal to 1.
Yes. Okay. So now in this case, as both the numbers that are equal, so we will have EQ equal to 1 and others outputs that will be equal to 0. Okay. So you can write in this way, you can write n number of combination input combinations. Okay. So and then from that you can test whether your circuit is giving proper output or not. That means whether your VHDL code is giving proper output or not, so that we need, that we can check. But now as we have considered three cases where GR is equal to 1 or EQ equal to 1 or uh, uh, LS equal to 1. So these three conditions that are we have considered. So we will have only these cases. Okay, so that means for these cases only we are checking this test bench. Okay, after that there will be a wait statement. So whatever are the final input conditions, that will be wait, that will be hold for the till the end of the simulation. Okay, then end of this process and end of the architecture. Okay, so this is the test bench code, test bench for the very comparator circuit. Okay, and when we are simulating this, we will get this type of output waveform. Okay, so here you can see that A, that is initially we have assigned a 4-bit value, that is a, it is a 2, in a decimal it is a 2 and B is 9. So you can see that here this is the A and B. So actually this is a bus structure. Okay, and in that case as A is less than 1, so sorry, A is less than B, so you will get LS, that is 1. Okay, EQ that is 0 and GR that is also 0. Okay, so you can check this result whenever A is 2 and B is 9, that time LS is 1, EQ that is a 0 and GR that is 0. Okay, when we after 2 nanoseconds this will change the values and now A is 9, B is 2. So in that case LS is 0, EQ is 0 and GR that is 1. Okay, and then after that finally we have uh, both these numbers, that is A and B, both are equal, so that are 10. So in that case you will get LS is 0, EQ is 1 and GR that is 0. Okay, so this type of result that you will get when you simulate this program. Okay, and these values here, whatever are the values that are shown, these will be the final state of these inputs and outputs. Okay, हे जे काही फायनल स्टेट कंडिशन असणार आहे, तुमचं जे इनपुट असणार आहे इनपुट स्टिम्युलस, त्याच्याप्रमाणेचे जे रिझल्ट्स आहेत दॅट विल बी डिस्प्लेड ॲट दिस व्हॅल्यू. ओके, so but when you are simulating actually this program, whenever you click on any at any time, okay, on these waveforms you will get at that result at that instance. Okay, so that will be displayed at this value column. Okay, so this is the value column which will be related with this timing. Okay, so this value, that is the final value of the inputs and outputs. Okay, so remember that now बऱ्याच जणांना प्रश्न पडला असेल की जेव्हा मी म्हणते की इथे 2 आणि 9 आहे तेव्हा इथे 1 आहे, 0 आहे, 0 आहे, बट हे जे काही रिझल्ट आहे तो फायनल रिझल्ट आहे इथला, जो काही फायनल इनपुट्स असणार आहेत आणि त्याच्यावरून जे काही तुम्हाला फायनल आउटपुट मिळणार आहे त्याचा. ओके, सो दिस इज द test bench for comparator. Okay, so all of you understood this code?
Yes, ma'am.
Any doubt about this? Pradnya? Any doubt?
No, ma'am.
So, uh, again, so that means I think now is it clear for you to how to write test bench for any circuitry?
Yes, ma'am.
Okay. So let us proceed and let us go for the another circuitry, that is the encoder. Okay. So first of all, now you write code for 8 as to 3 encoder. Okay. So that means we will have a encoder which has 8 inputs and 3-bit output. Okay. So write a VHDL code for 8 as to 3 encoder. Now what is mean by encoder?
Encoder
What
is
is
a
mean by encoder?
combinational circuit. Encoder is a combinational circuit which encode the input data.
Yes, encoder, it is a combinational circuit that encodes the uh, input data. Okay, so that if there are 2 raised to n number of inputs that are present, then we will get n number of outputs. Okay, so for 8 inputs are there, we will get 3 outputs. Okay, so actually this could be a number where we can convert octal to binary. Okay, so now um, write a code for this encoder. Write VHDL code for encoder circuitry, and then we will discuss about how to write test bench for this. So let us have 3-4 minutes to write this code. Completed?
No ma'am, architecture लिहिते.
Okay.
Completed ma'am.
Okay. So now let us check it. Okay. I hope you have written this code in this manner. So the first, that is a library declaration. So which library we need to declare here? That is a
IEEE.
IEEE. Yes. Okay. And the package that we are adding is a std underscore logic underscore 1164. Okay. All the functions which are available in this package that we are adding in this code. Okay. No another package that we are adding. So these two are that are sufficient for this. Okay. After that, this will have input ports that are 8 input ports. So D0 to D7, which are of the type that is a std underscore logic, or it is a bit. Actually, it should be a std underscore logic bit, because in a Xilinx it will take it as by default it will take it as a std underscore logic. Okay. So after that, end of this entity, and then architecture for this entity, that is now as we have three output ports, that is a x, y and z. Okay. So x that is assigned to the expression, that is d4 or d5 or d6 or d7. Okay. This is the boolean expression that you will get from the truth table for this encoder. Okay. Y that will be assigned to d2 or d3 or d4 or d7, and z that will be equal to d1 or d3 or d5 or d7. Now you will observe from these equations that d0 is no anywhere considered, okay, in this boolean expression for x, y and z. That means whenever d0 is equal to 1, it will take the value for that as equal for all the x, y and z, all variables that will be equal to 0 only. Okay, so this is the end of encoder um, architecture. Okay, so it encoder 83 architecture. So all of you got this code only, or all of you have written in this way only, or something different that you have written?
नाही मॅम असंच लिहिलंय.
Okay. Now remember that actually whenever we write expression, that time we write it as a d4 plus d5 plus d5 6 plus d7. Okay, that means for ORing operation we use sign that is a plus whenever we are writing boolean expression. But when you are writing code, that time you need to use a keyword which is uh, specified for the ORing operation, and that is OR. Okay, so you need to write here, instead of write a plus sign over here, you need to write OR, then only this code will get executed, otherwise it will show error. Okay, so you have to write this as a OR only. Okay, so this is the very VHDL code for encoder circuit. And now let us move towards the architecture. Okay, so once when you are writing test bench for this encoder circuitry, that time what will happen? You need to associate that entity, whatever is the VHDL code that you have written for encoder circuitry, that you need to associate with this test bench. Okay, and once you associate with that that entity, then this library declaration and entity part and architecture part, that will automatically come, which will be related with that entity. Okay, so library declaration, so for this test bench, that is a library IEEE, then package that will be added, then after that entity for this test bench. Okay, so I have given the name for this entity as a enc83 underscore tb, and then as here, as I have already stated so many times, that whenever we are writing a test bench, that time for the entity of that test bench you need not to declare ports. Okay, so no any ports that are declared end of that entity. But remember that though we have not declaring any port names here, but we need to write this entity. Okay, so starting of the entity and end of the entity, that must be there. Okay, so that is part of this uh, VHDL code. Okay, after that we are writing architecture for this entity. Okay, so and architecture behavior of this entity, that is the ENC83 underscore TB is, and then we are here going to use the component. Okay, which component that we have written in the VHDL code of encoder. So तिथून जो काही create होणारे component that we are going to use in this architecture. So component ENC83 that has the ports, that is from D0 to D7, which all are the input ports and are of the std underscore logic type. That means all are a single bit input ports. Okay, and after that outputs that are x, y and z, again all are output ports and of the type std underscore logic. Now here, as all the ports of this components are declared, so end of this component. Okay, then we need to initialize the signals. Okay, so input signals are D0 to D7. Okay, and all are of the standard logic type, and all are initially having the value that are 0. Okay, so that we are initializing here. Okay, for each of this signal we will keep this input values to 0. That means actually we are resetting the component encoder that we have used in this architecture. Then outputs that are again we are initializing it as a signal, that is the x, y and z, all are of the type std underscore logic. Okay, and then we are beginning with the actual architecture. So instantiating unit under test. So that is a whatever unit that we are testing here. Okay. So for that, first of all, we are going, this is the unit under test which we are going to map with the component that is the ENC83, and we are mapping the ports here. Okay, so for that we are using a keyword that is a port map. Okay, so port map. So here D0 to D0, D1 to D1, and up to D7 to D7. So all ports are mapped, as well as all output ports are also mapped accordingly. That is the X to X, Y to Y, and Z to Z. Okay, so we are giving the names to the ports which are available in this test bench, as well as to the ports of the कंपोनंट दॅट वी हॅव यूज. ओके, सो प्रत्येक जे काही पोर्ट्स आहेत ते आपण मॅप करून घेतो इथे. आणि आत्ताच्या ज्या एंटिटीसाठी, म्हणजे आत्ताच्या जे टेस्ट बेंच साठीचे जे पोर्ट्स आहेत ते आपण सेमच नेम घेतलेत. दॅट इज नॉट मेकिंग मच डिफरन्स. सो हियर वी हॅव यूज दॅट सेम पोर्ट्स. ओके, सो आफ्टर दॅट ऍक्च्युअली द टेस्टिंग प्रोसेस. सो जी काही प्रोसेस आपल्याला लिहायची आहे, ज्याच्याप्रमाणे आपण टेस्ट करणार आहे, सो दॅट विल बी हियर in this process. So that is a the name given to this process, that is the steam underscore process. So that means it is a stimulus process and beginning of this process. So initially we will hold whatever is the reset state for 100 nanosecond. Okay, so after, for that we have used the syntax, that is the statement, that is wait for 100 nanosecond. So it will wait for 100 nanosecond, and then after that whatever inputs that we are going to give, that will be executed. Okay, as you know that process that executes the all statements in a sequential manner. Okay, though VHDL is a concurrent language, that means statement, different processes that we can execute parallelly, but whatever are the statements in the process, that we execute sequentially. So once this wait for 100 nanosecond, that statement is executed, then it will consider the inputs. That is, now we have assigned value for D0, that is 0, D1 1, D2 0, D3 0, D4 0, D5 0, D6 also 0, and D7 also 0. Okay, now while discussing about the encoder in earlier lecture, we have already said that whenever we are considering encoder, that time we assume that only one input will be high at a time, others will be at a zero. Considering that only, I have given the, I have written this input stimulus. Okay, so now these will be the states for the inputs, and after that we can have wait statement. Okay, now that here these values can be wait hold for a certain time. That is, you can use the statement, that is a wait for 10 nanosecond, and then you can initialize some more different cases. Okay, so that means different combinations for the input. But while writing this program, I have written here only once. Okay, so that means in a PPTs I have mentioned it is only one combination, but actually while executing this program, I have taken so many another cases also. So in a output waveform that you can see. Okay, after once you finish whatever input that you want to give, there will be a wait statement. So whatever are the last values, that will be hold. Okay, then end of the process and end of the architecture. Okay, so this is the test bench for 8:3 encoder. ओके, मी परत एकदा सांगते की मी इथे एकच केस कन्सिडर केली, पण इथे तुम्ही वेगळ्या केसेस घेऊ शकता. आणि वेगळ्या केस जर घ्यायचे असेल तर तुम्हाला काय करावं लागेल, इथे परत हे तुमचे सगळे इनपुट कॉम्बिनेशन झाल्यानंतर त्याच्यानंतर तुमचं काय येणार आहे, wait for suppose 10 nanosecond. That means it will hold these values for 10 nanosecond, and then it will go for another case. तिथे तुम्ही परत वेगळे कॉम्बिनेशन लिहू शकता. म्हणजे त्या केस मध्ये तुम्ही लिहू शकता D0 equal to 0, D1 equal to 0, D2 equal to 1, then D3, D4, D5, D6, D7, 0. ओके. दुसरं कॉम्बिनेशन घेऊ शकता की ज्याच्यामध्ये D3 1 करताय, बाकीचे सगळे 0 आहेत, किंवा D5 1 करताय, बाकीचे सगळे 0 आहेत. सो ऑल दीज कॉम्बिनेशन दॅट यू कॅन हॅव इन दिस. ओके. आतापर्यंत आपण आता जेवढे सगळे टेस्ट बेंच बघितले, त्याच्यामध्ये तुम्ही बघितलं असेल की इथल्या टेस्ट बेंच मध्ये कुठंही तुम्हाला आउटपुट नाही दिसणार आहे. ओके. आउटपुट साठीचं एक्सप्रेशन दिसत नाहीये, बरोबर आहे ना. तर why it is not written? Because we have associate. This is just a stimulation process. म्हणजे जे काही कॉम्पोनंट आहे त्याचे काय इनपुट्स आहेत ते आपण दिलं, आणि त्या कॉम्पोनंट मध्ये आपण ऑलरेडी आउटपुट्स असाइन केलेले आहेत. म्हणजे जेव्हा तो कॉम्पोनंट आपण या सर्किट मध्ये किंवा या कोड मध्ये आपण कॉल करतोय, ओके, आणि त्याचे जे आउटपुट्स आहेत त्याच्या तेच आउटपुट याचे पण असणार आहेत. तर ते आपण इथे सिग्नल्स मध्ये असाइन करून घेतलेले आहेत. सो त्याच्याप्रमाणे आपल्याला आउटपुट मिळेल. सो ही झालं आपण एकच केस आता इथे कन्सिडर केली, पण ऍज आय सेड वी कॅन राईट इट सो मेनी इनपुट कंडिशन्स. ओके. अँड देन हिअर व्हेन यू एक्झिक्यूट दॅट कोड दॅट टाइम, ओके, यू विल गेट दिस टाइप ऑफ आउटपुट. ओके. सो इथे जर तुम्ही बघितलं तर पहिल्या 100 नॅनो सेकंड इथे I have considered 10 nanosecond period while executing this. So for the first reset condition, that sorry, it is a 100 nanosecond. 100 nanosecond, this will be hold for the values, that is all the values that are 0. Okay. So depending on that, you will get the result, that is x is equal to 0, y equal to 0, z equal to 0. Okay. For next 100 nanosecond, it will have the value, that is D1 is equal to 1 and all other inputs are at a 0 logic level. So at that time you will get result, that is 0, 0, 1. ओके. पुढचे कंडिशन काय आहे की D2 1 आहे आणि बाकीचे सगळे 0 आहेत. तर या केसमध्ये तुमचं आउटपुट काय यायला पाहिजे, करेक्ट आउटपुट काय यायला पाहिजे जर D2 1 आहे आणि बाकीचे 0 आहेत, म्हणजे what should be your
1
output?
0 1 0.
0 1 0. Okay. So that should be output. If we check it, we are getting the correct. So x is 0, y is 1 and z is 0. Okay. Now can you explain about this condition? Now in this condition, what is input conditions?
D3 is equal to 1, so that 0 1 1 output is there.
Yes, yes. Okay. So now if you check for all other conditions, then you will find that we are getting the correct result. Okay. म्हणजे इथे आता last condition, D7 is 1 and all other inputs are 0. So we are getting output, that is a 1 1 1. Okay. And that is displayed over here. Okay. म्हणजे इथे सुद्धा तुम्हाला दिसेल या व्हॅल्यूज मध्ये this is the final state. So it is a 1. D7 is 1, all others are at a 0. So all outputs that are 1 1 1. Okay. So this is a result of the execution of test bench code for a test to 3 comparator. Okay. So anybody has doubt about this?
No, ma'am.
Okay. Everyone understood this? Nikhil, any problem? Okay. So in the next lecture now here we have not considered clock. Okay. असं कुठलंही सर्किट आपण कन्सिडर केलं नाही की ज्याला क्लॉक लागणार आहे. Okay. So in the next lecture, let us discuss about the circuit if possible. Okay. Otherwise we need to again discuss about some more circuitry. So that will require clock also. Okay. So we will write a test bench for some different circuitry in the next lecture. Okay. We have few more minutes, so if anybody has any doubt, they may ask.